Yesterday we were going through the quiz, the first quiz number 1, really touch base on those common mistakes that have been seen in calculus classes. And I also told you that there are bits and pieces of quiz 1 that will be on the exam because we cover them throughout the semester. So we ran up to number 17. So let's look at number 18. Okay, so if you have any questions, so please don't hesitate to ask me your questions. Okay, number 18. Number 18 is this question. It says, if x is larger than 0, and a is larger than 1, okay, so the domain issue is no longer a concern. We have ln x over ln a is equals to ln x divided by a. So we don't have the worries that the denominator will be 0. So it just, in general, what if this is true? Is this true? Right? Is it true? Well, we have to understand the flow. Once again, it's a flow, right? A lot of people, actually, this is a very, very, very common mistake, okay? Because ln is a function, ln is a function. So when we look at this, this claim, okay, this is a claim. This is a statement, okay? This is not an equation. This is a claim. This claim says, if, okay, on the expression on the left-hand side, what it means, okay, by order of operation once again, okay, order of operation once again. So we have these two expressions, right? So the input is x, and then the function is ln x, and these two could work at the same time, parallel. Okay, so ln a, okay? And after both are done separately, and we're looking at ln x divided by ln a. Okay, so that's the flow. Okay, that's the flow. Okay, the order of operation. And the other one, however, okay, and surely we have x as input, we have a as input, and we will do the division first. So x divided by a, and then we work on ln of x over a. So that's the order. That's the order. Okay. So the question is, are these two the same? Right? The question is, are they always the same? Are they always the same? Right? Which come to is true, always true. False once, false. Right? So you'll be thinking about naturally, right? Naturally. So is there a counterexample? Because usually if it's false, there should be a counterexample we can find. Right? So for a larger than 1, so let's try to find, let's see if we can find a counterexample, right? But we can also apply some other properties we know. For example, okay, so we'll be thinking about counterexamples, or maybe there's some existing rules, right? And there are existing rules that we could, simplify left or right? Well, we do. That's a quotient rule, isn't it? Just ln x minus ln a. Okay, that quotient rule, the statement about that quotient rule is this. Log base b of one quantity over the other is the same as log base b of capital A minus log base b capital B. Okay, everything in the domain. So then the question is, if this is true, we guarantee that is true because that's a quotient rule. Is ln x minus ln a the same as ln x divided by ln a? Right? Okay. So this process, is equivalent. Okay, it's equivalent to that ln x minus ln a. Are they the same? Right? So we know that these two processes, right? ln x minus ln a, ln of x divided by a. So these two are the same. So this is true. Okay, this is true. If this is true, that means we're comparing these two processes. Are they the same? Are they always the same? Right, we still need a counterexample. If they don't look like they might be the same. So let's try to find some counterexamples. Okay, let's try to find some counterexamples. Okay, so within the realm of that specification, right? That within the realm of that specification, let us assume A equals to E, right? Make it easier to calculate. How about we make x equals to E squared? We just play around with it, right? We just play around with it. And the left-hand side, right? The left-hand side would be ln E squared. Okay, ln of E squared. The denominator is ln E. So we have 2 divided by 1, and which is 2. That's the left-hand side. Okay, I don't know if this counterexample will work. Okay, and the next one, okay, the right-hand side. Okay, so we have ln, okay, E squared divided by E, right? What would that be? Ln E, right? Ln E, because E squared divided by E is ln E. Ln E equals what? 1. Left is not the same as right. So this will serve as a counterexample. So in this case, it's false. Thus, right? In this one case, it is false. It is false. Thus, it is false. False one's false. False one's false. Right? Do you see that? right? So that's number 18. That's number 18, right? So we follow that principle that if it's true, it has to be always true, no matter what example within your constraint, it has to be true. False once, false. Okay, so let's look at 19. 19 is the mistake that we have addressed over and over again in class, but this is a very common mistake. Right, if we look at the deriving of the quadratic formula, then we know that this is certainly a mistake, but this is a very, very common mistake. It's a very common mistake. And similar mistake could be, 3x and 3 times sine x. It could show up in many different shape and form. It doesn't have to be 2. It doesn't have to be 2, right? So this is a terrible mistake. But how come people make such mistake? Right? Because these mistakes are typically seen in a calculus class. So that amount, that you see that it shows the severity of such a class. It shows the student doesn't know this fact. This is a truth. This is true, being proved. This is true. This is a common mistake. This is a common mistake. Okay. Do we have a counterexample for it? Okay, so we really will never make such mistake. Okay, counterexample. So let's make a counterexample, right? Let's make a counterexample. Say I assume x equals to pi over 2. I'm just trying some random examples, right? Easy to calculate, right? And the left-hand side would be sine of 2 times pi over 2. Okay, put them in the parentheses. And that's a sine what? Sine pi, right? It's also, it's from the flow, okay? It's also, we look at the flow afterwards. And sine pi is 0. And what happened on the right-hand side? So from every perspective, from the formula, from counterexample, so now this week we're going to use the pi over 2, right? And 2 times sine pi over 2 is 1, so that equals to 2. And 0 certainly is not equals to 2, right? Left is not the same as right. Left is not the same right. So I pointed to all these different aspects so that you're not going to make that mistake. We're not going to make that kind of mistake, right? So counterexample. Left is not the same as right. So in this case, we talk about when x is pi over 2, it is false. False once, thus it is false. False once, false. This is false. This is a statement you cannot use. The other perspective is the flow. The flow. Look at the flow, right? So we have this, if you look at the flow for these two cases, right? Let's look at the flow, right? You must understand the flow. Okay, if you in STEM major, you're gonna suppose you use some math in your programming, you have to understand the flow. So the flow is very, very important. Okay, so x is the input, so you do the 2x, and then you apply the function to sine 2x. And this other one, you have the input, you apply x, I'm sorry, you apply sine rule to it, and then after you get the output, you multiply 2 sine x. And I want to give you one more perspective. Okay. The one more perspective we're seeing here is also reflected in this example. Okay, what is it? Okay, another perspective. Another perspective from the domain and range perspective. Okay, we know that sine of anything, any angle is always between +1 and -1. And of course, if this anything is 2x, it's between -1 and 1, right? So that for any x, real number, right? Any real number x, okay? And now still sine of anything, because of the flow, right? Sine of anything, it's always between -1 and +1. Okay, how about 2 times sine? So you multiply by 2, multiply by 2, multiply by 2. So 2 of sine x is going to be between -2 and +2. This will give us a guideline as to how to find that counterexample if that's what you're looking for. So from all these perspectives, right? From the formula perspective, if you know this formula, then you know something was missing here. That's already tell you, hey, don't use it. It's not true. And very quickly you can pick up a simple example is to testify, because if it false once, it's false, so you cannot use it. And you look at the flow, and you look at the domain and range from all these different perspectives. Of course you're not going to use it. Of course we're not going to use it, right? So that's number 18. That's number 19, sorry. Number 20. Number 20. Okay. It says we actually have numerous examples of similar sort. Tangent inverse of a -1 is equals to 3 pi over 4. Okay, so what is the argument? Why is it? Okay, this will be related to the arctangent or tangent inverse, right? We talk about the truncation. They're all one-to-one functions. So this cannot be, well, why is this false, right? The argument, and of course, the typical argument would be, oh, because tangent 3 pi over 4 is equals to -1. Right? Because tangent 3 pi over 4 equals -1. The answer, of course, that answer is not strong enough. Why? Because tangent inverse must be a one-to-one function. Okay. And the powerful, we have several powerful reasons, right? Our reason, first of all, this is a false. Okay, this is a false. Common mistake. Why? Because tangent is a one-to-one function. And its range, okay, this range is imposed on, okay, after truncation. This range is imposed on. This range is between -pi over 2 and pi over 2. That's the range, okay? So we have the entire section about the truncations and so on and so forth. So this is false. Typical mistake. 21. Okay, 21. All these examples demonstrated the student did not have adequate preparation in trigonometry. Okay. We can see where this comes from. Okay, we can figure out where this comes from, right? We can figure out where this come from. Cosine inverse of x. There's no such a thing. There's no such a thing. Okay, it is false. Okay, it is false. So why student makes such a mistake? The reason seem to be very reasonable. Okay, the reasons seem to be very reasonable because tangent of an angle is equals to sine x over cosine x. Okay, tangent. All right. So how do we demonstrate this is false? How do we demonstrate this is false? How do we demonstrate this is false? Okay. Well, from domain and range perspective, the domain, there are all these, of course, first we can start with the flow. Right, so just because of that, it doesn't mean you take inverse on both sides. I understand this mistake is so common. This mistake is so common, right? So let's look at tangent inverse. So what is what kind of flow? X is the input. What kind of input is it? Ratio, right? Ratio. So we are going to, so X is from here. I'm trying to find that symbol. Okay, X is a ratio. It is from negative infinity to positive infinity, right? You guys should be pretty familiar with the domain and range for tangent inverse and what comes out. So this is going to be an angle. This angle is going to be in the range. Okay, we just talk about the range. What is the range? The range will be from negative pi over 2 to positive pi over 2, exclusive. Exclusive does not include the endpoints, right? So we've done all the graph and all of that stuff. That's the flow. And the other one, right? So this flow is like that. This other flow, right? Well, how about this flow? This other flow. This other flow, we have to study the domain and range. We have to study the domain and range, right? Yes, you're going to have two functions operating at the same time, but we have to guarantee the denominator is not a 0, right? So X serve as the input, right? So sine, right? And then cosine, work on it. But we have to be aware of this, the domain and range for the domain for sine. Okay, it requires the X has to be between -1 and 1. Remember that? Okay. let me put it under. Okay, the domain and range for sine, it has to be between -1 and 1. The domain and range for cosine, it also has to be between -1 and 1, all right? So for sine inverse, which is arc sine, those x, the input, okay? This x has to be between +1, -1. Ratio produces angle, right? For cosine inverse, is the same thing. Okay, cosine inverse. But because cosine inverse, so these x's you use has to be between -1 and 1, and these x you use can be any real number. So how do you coordinate that? Even if you choose x between -1 and 1, you have to make sure this is not going to be 0, right? This is not going to be 0. One is a cosine inverse equal, remember the range. Okay, so let's go back to the range, right? So the range of cosine, this is the opportunity of review, right? The range of cosine is between 0 to pi. Okay, and sine inverse is, it can be, because it's on numerator, so it can be it can be, you know, it can be 0. It's just that wouldn't matter. So in order to guarantee, okay, so in order to guarantee we don't have a denominator, we don't have a 0 denominator, that is a cosine inverse of cosine inverse of angle is not going to be 0. We have to make this greater than 0. Make it greater than 0, and that means it cannot be 1, right? So this piece of x, you have to make adjustment to that. So you're gonna have to make some adjustment. So this is gonna be from -1 to 0, because cosine 0 equals to 1, right? Cosine 0 equals to 1. Oh, sorry, +1, not including 1. Okay, so the x you're getting, right? So from the domain's perspective, you can see it is simply a mess. It's simply a mess. On the one hand, tangent x can take any real number, and to operate on this one, x cannot be, it has to be between -1 and 1. And the denominator has to be between -1 and 1 without including 1. That already tells you, hey, this is a no-no. This is a no-no. Okay. So if you still want to push forward, right? You say, okay, tangent x, this x has to compromise, right? This x has to change from -infinity to +infinity to comply with that. So even this is satisfied. Okay, so let me finish the flow, right? Let me finish the flow. Okay, so you can see what a mess has been created and reflected this particular student's misunderstanding of trigonometry and in basic level. So even if, okay, even if we make all three parties happy, right? We choose x between that, okay? We have taken care of everything. Will this be true? Even with this restriction, will this be true? Right? Will that be true? Do we have a counterexample? Do we have a counterexample? Do we have a counterexample? Okay, you see from what we just analyzed, let me just leave some space here. Okay. from what we analyze, we need to take care of the domain, and we need to make all three parties happy, right? If tangent x can be the x can be chosen from any number, any real number, then certainly it's okay to choose numbers between -1 and 1 without including 1. So even under these circumstances, is it true? Right? You see how I peel it over, peel it from a layer by layer, right? So let's find a counterexample. Okay. So what I'm going to choose x equals to 1. Okay. Oh no, x cannot equals to 1. Oh, wait a second. X cannot equals to 1, right? X cannot equals 1. So I'm going to choose x between -1 and 1. How about I choose x equals to -1? I can choose x equals -1, right? The reason I'm doing this because I want to make the calculation a little bit easier, isn't it? Right. So if I choose x equals -1 on the left-hand side, okay, x equals to -1. What does this equal to? This equals to -pi/4. Okay. How about the right-hand side? Okay, I don't know if this is going to work. Okay, just to work through it. Okay. Even if this works, it doesn't mean it is true, because okay, that's the other thing I wish to demonstrate. Even if this works, sometimes you have an example, if one example it works, it doesn't mean it is true. So this is a -1, and this is a -1. Okay, we see what we're getting. Okay, what is sine inverse of -1? That's -pi/2, right? Is that -pi/2, right? Cosine inverse of -1, what would that be? What would that be? That's a pi, isn't it? And when you divide -pi/2 by pi, what do we get? We get -½ So even under the most stringent circumstances, right? You can see we just randomly pick an example. We pick an easy example. Left is not the same as right. Left is not the same as right. Think about that, okay? So this is false once. False. Okay, so please don't make these mistakes. They look so intuitive. Yes, for someone who doesn't have adequate preparation in trigonometry, this looks very intuitive, but please please don't make such a mistake. So we cover 20, 21. Okay, 22 through 25. 22 through 25, right? So these are related to logarithms. Okay, so I'm going to excuse myself just for a few minutes. I'll be right back. All right, so let's look at number 22. 22 through 25 are the mistakes we have seen over and over. And we have definitely addressed them in classes. So okay, let's look at some examples. We have log base b. Very common mistake. Okay, we know that all of these are mistakes. But when these mistakes applies to Okay, so oftentimes when we see these mistakes are not showing up exactly as it is. These mistakes will show up for different bases. For example, typically, okay, looking forward to your calculus class, it'll be something like this. Look how natural that looks, right? It could be something like with the common log, right? Look how natural it looks, but they're all false. Okay, so this is a false, and that is false. And of course, that is false. It doesn't matter which base. It doesn't matter what base. Okay, and the most popular one, of course, will be base 2. If you like to take a look at in the base 2 situation, and we need to be able to recognize these falsehood. We need to be able to recognize these falsehood. Okay, so the false show up on different with different face, right? Base 2. For all of these cases, we should be able to have counter examples to counter them. Okay, and okay, number 23, right? The subtraction case, same thing. The subtraction case. These mistakes also show up. Okay, also show up. And number 24, we can come back to it, right? We can come back to it. Today, actually, nobody show up. So I suppose that I'm going to leave these recordings and you guys are going to watch. Okay, so log base B. Okay, A over B is equals to log base B. We had a similar example, this one over here, log base B of capital A, log base B of capital B. We had a similar example on 18. 18. Okay, what was 18? We just went over it, right? It's ln x over ln A equals ln x over A. Okay, so please refer to that example where, of course, x is larger than 0, A is larger than 1, right? You can see that this case, this falsehood, right? So we have a special case already covered. The special case on 18 of this quiz. Okay, the special case of that on 18. Okay, so that's 15. I'm sorry, 25. 25 is the same thing. 25 is the same thing. 25 is the same mistake and made on common log. You guys see that? So this mistake could show up in different shapes and in different faces. Okay, one day it wear the color of natural log, another day wear the color of common log, but they're all mistakes. They're all special cases. Okay, so this is a special case. Okay, so let me just write it down. It's a special case of 24. It's a mistake. So this is a terrible mistake. Okay, So to enhance these common mistake, to enhance the understanding of these common mistakes, and I'm going to put these all together, right? To look at some other perspectives from the flow perspective, from counterexamples perspective, right? For example, we had done similar examples on base 2, right? On base 2. So just don't make these mistakes. For example, on the 2's are the easiest to case situation to find counterexamples, right? So let's do a counterexample, right? I can choose A equals to capital A equals to 2, capital B equals to 2 squared. Why do I choose those? Because they're in a base 2 situation, it's much easier to handle, you know, these. So we have a left-hand side and we have a right-hand side. And we have a left-hand side and we have a right-hand side. We see if they're the same, okay? So this is going to be 2 and this is going to be 2 squared, right? By order of operation from the flow, so we have log base 2 of 6, okay? And let's look at this is 2 and that's 2 to the power 2. And obviously, right? And that equals to 1 plus 2 is 3. If we write 3 in logarithm form, is log base 2 of 8. Is left the same as right? Obviously not. So left is not the same as right. Left is not the same as right. Okay, not the same. So it is false. It is false. Okay, so you can say, so this is a false. False one's false. Okay, with one counterexample, we can claim that this is false. Right? If this is false, you can certainly find counterexamples. I'm going to, you know, you can go through all of these for each one of them, just to in order to avoid those mistakes, just for each one of them to give counterexamples, right? And I can give you something here as, you know, to get you started, right? So counterexample, right? Counterexample, I can choose A equals to 10, B equals to 10 squared. Okay, and we have left and right. Okay, so the left-hand side, right? And the right-hand side, the same drill, the same drill. The left-hand side is log base 10, right? Common log 10 plus 10 squared. And that equals to log of 100 plus 10, that's 110. On this other one, you have a 10, right? So we have a 10. So we don't need this piece. We don't need this piece. Just start with it, right? So this is 10 squared equals to, right? Equals to 1 plus 2. 1 plus 2 is 3. Yeah, if you write it in log form, it's log 1000. Is log 1000 the same as log 110? They're not the same. Of course, they're not the same, right? And the last but not least, and these are just ideas of examples, right? So you can have A equals to E, B equals to E squared. Okay, so ln, so left, right? And that's left, and we got right. So as you get better, mainly we just want to leave an impression on you that these are mistakes, and meanwhile, get familiar with those properties. Okay, so here, ln e plus e squared, can you combine them? No, you cannot combine them. Okay, you cannot combine them. And this piece, right, you have 1 plus 2, that's a 3 again. And if you write it as, you know, logarithm form, e to the power of 3. So the question is ln e to the power of 3 equals to ln e plus e squared? Is e to the power of 3 equals to e to the equals to, right? So the next question we need to answer, e to the power of 3, right? E to the power of 3 is e times e squared. So our question becomes, is e plus e squared the same as e times e squared? Of course they're not, right? E is a number between 2 and 3. So you can just punch in a calculator to see at this moment, are they the same? No, they're not the same. Okay, so left is not the same as right. Left is not the same as right. Okay, thus this is false. You see how, so this is false. Okay, just don't make those mistakes. Okay, all the examples we have applied for a plus, you can get similar examples on subtraction. And of course, at that time, you need to make sure a minus b is also larger than 0. So for example, you may choose for this case, you know, for counter example, right? You may choose capital A equals to 2 squared, and capital B equals to 2, right? And let's see if the left and right is the same. Okay, let's give it a try. Okay, and otherwise, so right equals to that, and left. Okay, so we have 2 squared here, and there's a 2 here, and we ended up with a log base log base 2 of 4 minus 2 is a 2 equals to 1. And the right-hand side, let's look at the right-hand side. We have a very interesting situation. We have 2 minus 1 equals to 1. Left is equal to right in this case. In this case, can we say, just because this example says it's true once, can we say it's true once is always true? The answer is no. You just haven't found the example. You just haven't found the right counter example, okay? This is very important. True once it does not mean true always. Okay, so please understand that. False ones, false. But true ones, it does not mean true always. So you cannot use this you cannot use this example which agree with the general statement. i.e. you cannot use anecdotes to prove prove the drug is working for everybody in the drug industry, for example, right? Suppose I take this medicine, it works for me. Does that mean it's going to work for everybody with the same condition? Not necessarily. So we cannot use that. That's a flawed logic. That logic is flawed. We just didn't find the example. So let's try another example. Let's try another set of examples, right? So we have to try more. We have to try more. Okay. So we have our left and right set out. Okay, so this is left and that is right. Right? So we keep looking. We keep looking. So how about I'm choosing A equals to 2 to the power 3. I'm choosing B equals to 2. I don't know. We just try it, right? We just try it. So 2 to the power 3 minus 2. What do we have? We get log base 2. 8 minus 2 is 6. Next one. Log base 2 of 2 to the power 3 minus log base 2 of 2 equals to 3 minus 1 equals to 2. And 2, write it in logarithm form, is log base 2 of 2 squared, or 4. Is left equals to right. So we have one supports it, we have one that doesn't support it. What does it count? Well, false, one's false. Okay, so mathematical principles make it very clear. Okay, so in this case, left is equals to right is violated. So even though we have a supporting case and we have a not supporting case, right? You have one case to support it. It doesn't mean it is true. So true once, it does not mean true always. Okay, it's very, very important to understand that. Okay, it's very, very important to understand that. So, but we found the false case. We found false once, false, right? So this is what? This is false. This is false. It is false. Okay, so for the subtraction case, and you know, you can go for it. Okay, so I'm gonna leave this piece for you. I'll leave the rest for you. And on that cases, these are terrible mistakes. We have gone over these examples, so that should be sufficient, right? So by this time, we have covered all of 25 questions on the quiz number 1. As I said earlier, some of the bits and pieces, okay, some of the bits and pieces of quiz number 1 will show up on your final exam, Okay, so let's see what else can could I review for you? I'm gonna go over quiz number 2. Okay, I'm gonna go over quiz number 2 in the notes. Quiz number 2. Okay, this is on your notes. Oh, I need to make some adjustment. Okay. Oh, looks like I'm going to have to close that, restart my 180 notes. Okay. Quiz number 2, there's some key elements, there are key issues which are also common mistake. Okay, which are also common mistake. So this is on quiz number 2. Quiz number 2. Okay, quiz number 2. Quiz number 2, there are 2 boxes there. 2 boxes there. Okay, 2 sections there. Okay, the first section And of course, we need to read the question, understanding the assumption. So quiz number 2. Quiz number 2 says, suppose that A and B are real numbers. Okay? Are positive real numbers. Okay, these are the fine prints. Okay, that is A is larger than 0, B is larger than 0. Additionally, okay, I can keep that color. Additionally, A is larger than B. Okay, A is larger than B. Okay. State if the following statement are true or false. State if the following statements are true or false. Okay, these are simple derivings that you must know. Are you going to need them? Yes. Okay, you are going to need them when? Calculus. In particular, I foresee this is you're going to need these in a lot of situations in calculus classes, including calculus 1, calculus 2. Okay, no joke. Serious. The first one, right? We must read the fine print. It says A is larger than B. So under this condition, it's very important to read the fine prints, right? A is larger than B. A is larger than B. If you make a B minus A, what do we have? B is smaller, okay? Both are positive. B is smaller. B is smaller. So from here, from this condition, B minus A is going to be less than 0, right? So how about B minus A larger than 0? It is false, right? Right? Because from what's given, A is larger than B, therefore B minus A is less than 0, right? Does that make sense? Okay. Right, so let's look at the second one. So you see, in this process, you just need to do a little bit deriving. We just need to do a little bit deriving, don't we? Now, number 2. Okay, so this is false. Number 2, the statement says, under the circumstances, A divided by B is positive. So where do we get started? Oh, we always get started from what's given. Right? From that, and A is larger than 0, B is larger than 0, right? That's what's given. From that's given, how do we make A divided by B? Well, you divide both sides by B, right? From what's given, we divide both sides by B. B is positive, so we don't need to switch both sides. Divide that by B. So it's really just an algebraic operation. So B divided by b is equals to 1. So a over b is positive, is larger than 1. So a over b is positive. So this is why this is true. Right? You can see typically it's just a one-step deriving. Now, 3. Still from the same place. Right? Still from the same place. Can we say that a squared is larger than b squared? Well, sure, of course. If a is larger than b, a is a positive, b is a positive, then you square both sides, and this is going to be true, right? True. It's true, right? So deriving. So let's look at number 4. Number 4 is getting more interesting, okay? It says 1 over a is larger than 1 over b. Still from the same assumption, that was given in the question. Is that true? Is that true or false? 1 over, if a is larger than b, then 1 over a is larger than 1 over b. Is that true or false? Right? So I like to think about this. It's a little bit confusing for a lot of our students, but let's look at some examples. We can look at some examples, right? We can look at some examples. In other words, I'm heading for counterexamples, right? For example, we know that 3 is larger than 2, right? So we're heading for a counterexample. But how about 1 over 3 versus 1/2? It's reversed, right? It's reversed. Follow me? Okay. But the question is this, we just mentioned one false, well, false ones is false. False one. So this is a false ones. So this is what? This is false. Okay. However, so now we know this is a false. But is this always true? From here, is there something about this always true? Right? So from here, A is positive, B is positive. Can we say that 1 over A is always less than 1 over B under the circumstances? Is this always true? Is this always true? Is this always true? The answer is yes. The answer is yes. Okay. I want to give you a perspective. This perspective I want you to see is related to the function of f of x. It's a very important function. You're going to be using this function in calc. Okay, in its various forms, On this question, on this function, we studied this function, we graphed this function. If we look at x is larger than 0, because we're studying when a is larger than 0, b is larger than 0, a is larger than b. So we have a reason to only just look at one piece, right? We only look at this curve on one piece. 0 to 5. 1 to 5. Just for example, okay? So we only just study this piece. Okay, this piece. This is a decreasing function, isn't it? When x is larger than 0. It's a decreasing function. Well, the entire thing is decreasing function, but it has two pieces. So when we are talking about our specific situation, which is A is positive, B is positive, A is larger than B, we're really in the situation of just taking this one piece. We basically ignore the other piece, right? The other piece doesn't apply to us. What does this mean? This means that for any input, okay, for any input, 2 inputs, for example, okay, for any 2 inputs, suppose I have an input here, I have another input over here. Obviously, the heart is larger than the star, right? Yes, that's the input, right? The star is this much, the heart is this much. The heart is larger than the star. Okay, so let me write it down. Okay, so I'm going to put a little bit. Okay, so the heart is larger than the star. Do I have a star? There. Okay, the heart is larger than the star from the picture. What is the output? Okay, so let's look at the visual. Okay, the output for the heart, I'm going to make it yellow, right? That's the output. That's the output for the star. Okay, how about the output for the heart? This much. So what do we see, obviously? As the consequence, right, we don't need this row. As the consequence, insert a column, right? 1 over the star, 1 over the star. Which one is larger? 1 over the star is larger, right? Oh, where's my star? 1 over star is larger than what? 1 over the heart. Okay, so this is always true. This is always true. So what is always true? What is always true? In our situation, we have a B less than A. Okay, so let's translate, right, symbolically. So we have a B minus A, then 1 over B is larger than 1 over A. This is always true. This is always true. So this is the visual. Okay, this is visual. I promise you, you're going to use it. Okay, you're going to get to use it in your calculus class somewhere. All right, so that's number 4. Number 5 is true, right? It just powered by 3. Then you may be asking the question, right? What if both are negative? That's a good question to ask. That's a very good question to ask. Okay, still under the same circumstances. Let's look at number 5. If we power both sides by 3, a to the power 3 is going to be larger than b to the power 3. This is always true. So this is true. Okay, so under that circumstance, number 6, right? The statement is saying negative a is less than negative b. Is that true? Well, it's still from the same circumstances, right? Still from the same circumstances. If you multiply both sides by negative sign, by -1, what do we do? From here, if you multiply both sides by negative, you will switch the direction, right? So that number 6 is true as well. You see, all of these are one-step deriving, and we should be able to derive them. We should be able to derive them. Okay, so let's look at the second section, the second table in quiz number 2. Okay, second table in quiz number 2. Okay. Now, I'm going to bring this to the top. So we did the quiz number 1. We did the first table in quiz number 2. And let's look at the second one. The second table in quiz number 1, right? The first one. Who's the first one? You have A over B plus C equals to A over B plus A over C. Oops. What did I do? A over C. Okay, A over B plus A over C. Is this correct? Doesn't this look familiar to one of the questions in quiz number 1? It is number 6. Doesn't that remind us? Similar? Is it more general? Just be reminded of? Does that look familiar? Right? What is that familiar form we saw? X minus y equals to 1 over x minus 1 over y. Right? In quiz number 1. Okay. So that's it. What's the question number? Let me give you that question number. So you can go back there and review those lectures. And that's number 6. Right there. So you can see they are actually originated from the same place, even though this is a plus, this is a minus. I mean, minus is plus or negative of something, right? So this, of course, is a false. This is a false, right? But this mistake is very alarming, especially if it show up in a calculus class that shows really the deficiency in algebraic operation. And we can easily get counterexamples to this, right? And you can see it from flow, and of course, this is false. Of course, this is false, right? This is a false. And you can easily get counterexample. But is there something that's true about fraction? Yes, right? So suppose I have A and B plus C. And that would be B over A plus C over A. Okay, this is true. Okay, guaranteed. Guaranteed. This is the basic algebra, isn't it? Pre-algebra. Basic algebra. This is false. But if you flip over, it will be false. Okay, flip over will be false. Do we have counterexamples? Do we have counterexamples? Okay, so all these counterexample practice is try to encourage us to really see it is a mistake instead of, because some of the mistakes seem to be rather intuitive for our students. Okay, so let's go a little bit further. So I'm going to choose A equals to, I'm going to choose A equals to, really it doesn't matter, 4, A equals to 1, B equals to 1, C equals to 2, right? Just a random number. And the left-hand side is equals to So I'm still gonna set up the left and right. Right, still gonna set up the left and right. So A is 4, and B is 1, C is 2. So by order of operation, this is a 4/3, right? And the right-hand side, we have A equals to 4, B equals to 1, A equals to 4, C equals to 2. And what I got a 4 plus 2. That's a 6. Obviously, left is not the same as right? Left is not the same as right. So false once, false. Okay, so this is false, right? False once. False. So do not commit these mistakes, right? You can see this mistake show up in this form. This is, I would say, is a general form, and this would be special form. But there's something that is true. This is true. Okay, so let me box it. True. Okay. Number 2, maybe we get to finish this, right? Maybe we get to finish this. This time, A, don't be careful. In this case, there's a if A is less than B, then this mistake is very awkward. I already tell you this is a mistake, right? Then A minus C is larger than B minus C. A is less than B. So if you subtract C on both sides, you don't change the direction. This is a false. Okay. Only when we divide or multiply, only when we divide, when we multiply or divide by a negative number, do we switch the inequality sign. Okay, so don't do that. Okay, some people get confused. Only we multiply or divide by a negative number do we switch, we switch the inequality sign, right? Only then. So when you subtract, no, don't switch. Please don't do that. Okay, so this is a false. All right, so these are common mistakes. I think we're getting closer to the end. Okay, number 3 is already addressed, right? We have PQ, right? So we're not going to do this. A plus B squared equals to A squared plus B squared, right? And this is a similar example. It's already addressed many times. This is just with different symbols, right? That's a familiar case. You know that symbol is just a placeholder, PQ, right? And nobody should make these mistakes. Nobody should make these mistakes. And number 4, common mistake. Okay, so this difference in squares, and this is, of course, is a mistake. This is a mistake. Okay, this mistake you certainly can give counter examples, but you can also this is a false. Let me put it false. False. Okay, and counter examples, you should have it, right? We're not going to address this one. This one is particularly tricky. There are 2 different ways to demonstrate the falsehood of this. a statement. There are two different ways to demonstrate the falsehood of the statement. For example, if you look at the right-hand side, right, if you look at the right-hand side, right, the right-hand side, okay, the right-hand side, which is a squared minus b squared, if you factor, okay, you get a plus b times a minus b. And the left-hand side, is a minus b times a minus b. So you're comparing between these two. Are they the same? Of course, they're not the same, right? From this comparison, and you can tell, hey, they're not the same. They're not the same, right? Not the same. That's one perspective. Another perspective is just so easily counterexample. Okay, counterexample. For example, I can have a equals to, say, 5, b equals to 3, right? So left, right, left-hand side, right-hand side. Right-hand side, right? So 5, 3, and that's by order of operation. We do parentheses first, we get 2 squared. 2 squared is 4. Over here, we have 5 squared minus 3 squared. That's 25 minus 9, that equals to 16. 16 is not the same as 4, right? So left is not the same as right. So it all has something to do with the flow. It all has something to do with the flow. So from every aspect, right? This is a false. Okay, so we have 2 more to go, or 2 more to go. Okay. These 2 more to go, I'm going to bring them to the top. Okay, bring them to the top. Okay, the second table on quiz number 2. Okay, so these 2 mistakes are rampant, and they show up in different shapes and forms, right? For example, a plus b, and you definitely have seen them. You definitely have seen some of them. I think we have addressed these mistakes, right? So now that's number 5. Number 6 is turn into subtraction. Assuming everything is in the domain. These are false. Falsehood. And they are terrible mistakes. Okay, so I'm writing these words here, hope to get your attention and not to make these mistakes. Why? It seemed to be so intuitive, right? So not worrying about domain. So we work with A is positive, B is positive. How about that? Right? We just and make sure A minus B is positive. So I'm going to give you this counter example. A is 25, and I like this example because it makes it easier for the calculation. Okay, and B, no, A is 9, B is 16. How about that? Right? It's easier, right? Left, right. left hand side, right hand side, right? 9, 16. Order of operation, we get square root of 25. Square root of 25 is a 5. 9, 16 equals to 3 plus 4 equals to 7. Okay, and 5 is not 7. So left is not the same as right. Oh, wait a minute. Did I not start in the lecture from the tech Zoom? I guess. Okay, so let me just complete it. Okay. And I'm going to use the same example for the other one. You know, I made a terrible mistake here today. No wonder nobody show up, right? Left, right. Never mind. Left. We have reached the end of the class. Anyway, so here I'm going to make a switch. Okay, I'm going to make some changes. I'm going to use 25, 16, right? So 25, 16. 25, 16. Okay, so this we're gonna make it root of 9, which is 3. And this one is gonna be 5 minus 4, which equals 1, right? So once again, left is not the same as right. Okay, so you can see this is a false. It's false. Okay, and of course the other one is false. So I'm going to close this, and I apologize that today I forgot to turn on the other Zoom meeting. But luckily I have all the recording here, so I'm going to send it your way. And I will see you guys in the office hours. I'm going to see you guys in the office hours. Okay, I wish you the best of luck. Thank you for a great semester. Thank you.